Warning. The name of the talk is Going Down the Compilation Rabbit Hole. Now, you may have heard of a compiler, but you don't know what it does, maybe. Don't worry if you don't know. I'm here to explain that to you. And by the end of the talk, you'll get a bird's eye view of how intricate the rabbit hole that is a Golang compiler. So, who am I? My name is Richard Rowland. I'm from Tokyo, Japan. I thought I would be jet lagged today, but the coffee here in Italy is magical. I'm a staff at OKCoin Japan, a global cryptocurrency exchange. You may have heard of Bitcoin or Ethereum. We help you buy and sell them. I use my technical understanding to evaluate blockchains and determine if they're compliant to Japanese regulations. Outside of work, my hobby is photography. We were just talking about cameras together. I post a lot of Instagram. Please follow me if you'd like. And I'd definitely appreciate it if you could share some photo spots here in Florence. As a side project, I've worked on a method to semi-permanently store data in the blockchain and the P2P network. That's up on GitHub if you'd like to see. So I've given talks about compilers before, namely Python. I've given presentations at several Python conferences, including ones in Canada, Ireland, Portugal, and Japan. As I dug deeper into the Python compiler, I became really curious about how other programming languages handle compiling. Would other languages have different compiler structures? Are there compiler techniques that make other programming languages better? There are many popular programming languages, but I decided to investigate Golang. Why Golang? First, it's really popular. If you're going to be a developer, you've got to be trendy. Furthermore, Golang is relatively new, so I assume that its developers are aware of the problems with the compilers of older programming languages. So, what is compiling? In a sentence, compiling is turning a source code into an executable format. Just writing the Go program doesn't execute the program. You have to do some work to make it run on the computer. The compiler converts the code into a format understood by your computer. And compiling is done by a program called a compiler. It handles the conversion from source code to computer-native format. You may have heard of programs like GCC and LLVM. These are compilers. These are famous compilers that have been built extensively over time by numerous contributors. And compiling happens in Golang too. You do it every time you build a Go program with a command like this, go build main.go. So about the Golang compiler, Golang actually develops its own independent compiler. It doesn't use GCC or LLVM. The Golang project is open source, so you can see the source code on the official website. The source code contains many functions for Golang, including the standard library. You could see the compiler-related source code under source, command, compile. Before we go further into compilers, I'd like to talk about programming language execution models. So the famous two kinds of programming execution is compiled languages and interpreted languages. Basically, the generation of CPU instructions is different. In compiled languages, you first have the CPU instructions generated. And when you execute code, calling the code from binary, it's just the work is done for you. You just run the binary. Meanwhile, with interpreted languages, the execution, you first execute the code, and then you generate the CPU instructions. This is often seen in languages that use virtual machines. Now, here are some examples. So the compiled types include Golang, C, C++, Rust, Swift. You know these languages for taking your time to build, even running the first line of your project. Meanwhile, the interpreted languages include JavaScript, Python, and Ruby. You know these languages for being easy to get your hands on, but not too capable of heavy computation. We have both kinds of programming languages to use in different cases. Let's look at the pros and cons of both compiled and interpreted languages. For compiled, the advantage is that you get fast execution. But the disadvantage is that it takes time to compile, and you need to compile for each platform. You can't take a Mac binary to run it on Windows or Linux. You have to recompile them to your target platform. Meanwhile, with interpreted languages, the advantages are that you don't need to create a binary for each platform. There's a famous slogan for write once, run everywhere. That's pretty much interpreted languages. But the disadvantage is that the execution tends to be slower. And furthermore, there is a CPU and memory resource overhead for the virtual machine. So let's compare C and Go binaries. I mean, they're both compiled languages, so how different could they be? Actually, quite different. Let's first look at the binary size. In C, we have a hello world program for both languages. In C, the binary size is just 33 kilobytes. Meanwhile, with Go, it takes a whopping 2 megabytes just to print hello world. Why does it take so much space to execute such a simple command? Let's also look at the assembly instructions extracted with the object dump command. Here we can start to see why the C binary is smaller than the Golang binary. In C, there are only 22 lines of assembly. Meanwhile, in Golang, there are 140,000 lines of assembly. This is just to print hello world. These assembly commands contain system calls, which tell the operating system what to execute. With C, there are only 9 system calls. Meanwhile, with Go, there is much more, with 209 system calls. So why does Go make so many system calls? Well, there's the overhead of running the Golang runtime. I mean, there are Go conveniences afforded by Go runtime, including garbage collection, the Go routine scheduler, channel operations. So we pay for these runtime features by having a larger and more complicated binary. By the way, if you were here yesterday, there was a talk on the Golang binary by Yesus. Hi there. Very good talk. If you missed it, go check the archive. Okay, let's talk about the Golang compilers. Yes, it's in plural form. Well, before we talk about compilers, what is Golang? Well, it's actually 2 kinds of things. It's a programming language execution specification, and it's a program execution environment. But we separate these concerns. So if you're a programmer, you just have to worry about the specification. You have to type the syntax correctly and make sure you use the right keywords. Meanwhile, Golang is concerned about understanding your code and making sure that it runs on your computer. As a matter of fact, the Golang specs is available for anyone to see. The specs contain rules for Golang, such as what a Golang program should look like and how a Golang program should behave. We have notation, source code representation, constants variables, properties of types and values, blocks, declarations and scope, expressions, statement, built-in functions, packages, program initialization and execution, errors, runtime panics, system considerations, and type unification rules. So why does Golang have all these rules written out? The Golang developers want to make sure that the implementation doesn't become like the specs. It's like how HTML is standardized so that any browser vendor can read and implement them. It's not like, Chrome implements a feature and now that becomes HTML. So that means if you follow the specs, you could build your compiler, but you have to maintain it. So let's look at the different Golang compilers. We have GC, the official Go compiler. We have GCC Go, which uses GCC. And we have LLGo, which uses LLVM. Sounds great. Which one should I use? Well, there are caveats. For the Golang compiler, the official one supports the latest features. But with GCC, you could use up to Go version 1.18. and there's no support for generics. Now, as for LLVM, well, the repo died in 2020, and I'm only mentioning it here to demonstrate the difficulties of maintaining a compiler. Please don't use them in production. So, how would you actually use a different compiler backend? Remember the famous compilers that we mentioned earlier? They're not just for compiling C. They can take your Golang code too. These are front-end projects that convert your Golang into an intermediate representation that these compilers can understand. This conversion is handled by the front-end, such as GCC Go and LL Go. When Golang is turned into a format that the compilers can understand, the compiler handles the rest of compiling. These compiler front-end lets you take advantage of the incredible existing compiler infrastructure. You don't have to reinvent the wheel. So why do you use other compiler backends? Well, you might want to use optimizations not implemented in the official GC. You might want to target platforms not supported by GC. Or instead of static linking, you prefer dynamic linking of libraries. Or it could be a political choice where you want to make sure the implementation doesn't become the specification. So, let's talk about how Golang gets compiled. This is the main dish of the talk. So we mentioned a lot of compilers, but we're going to focus on the main implementation, GC, the Go compiler. So here's a bird's eye view. Here we have all the phases that a Golang source code goes through before it turns into a binary. We divide the compilation steps into the front end and the back end. The front end consists of turning the source code into an intermediate representation called the abstract syntax tree, the AST. In order to turn the Golang into AST, we go through 3 phases. First, there's lexical analysis, then there's parsing, and then there's a generation of AST. Once you get the AST, we then turn into the back-end process of the compiler. In the back end, we have middle-end optimization, walk, SSA, which stands for single static assignment, and machine code generation. First, there's tokenization, which comes with lexical analysis. So here we have a concept called tokens, which is a unit of meaning. For the computer, a Golang source code is just a bunch of text, and it doesn't really understand the meaning of the source code. That's why we have to divide the text into a group of meaning. So in tokenization, the lexer looks at the source code and identifies meaning. Those groups of meaning consist of user-defined names like variables, as well as Golang keywords like if statement, switches, case branching, what have you. Golang provides a package called a scanner. You can use this to scan your source code and divide it up into tokens. So here's a simple hello world program. While it looks pretty straightforward for the user, the compiler needs to divide it up into many discrete tokens. It will divide up into function declaration, the name of the function, the parentheses, the curly brackets, the package and the methods being called, and even the end of file marker. Now that we got these tokens, we have to form a relationship between these tokens. How do these tokens interact? What kind of procedures do you perform as a result of these interactions? The parser creates a graph called the AST, or the abstract syntax tree. What is an AST? The AST is how your source code looks in a graph. In this case, a tree graph. You have nodes that correspond to expressions, declarations, and statements. Rather than describing what an AST is, it's much easier to explain with an example. We're going to use a small example, one line of code, because the end result becomes quite sizable. Here we have a simple assignment of a variable with an equation x equals 2 plus 3 times 6. What would this look like as an AST? This is how we expand a simple assignment into an AST. On the left, we have the variable x. On the right, we have all the mathematical procedures. As a matter of fact, the AST is aligned in a way that respects the order of calculation. That means we traverse to the bottom of the AST and compute 3 times 6 first. Then we add that with 2. Finally, we assign the resulting value to the variable x. In computer memories, you won't have these ASTs in graphic representation. GoLang stores these AST in memory as a series of nested text. If you look at a single line of hello world as AST, it becomes pretty complicated. It becomes harder for the human to understand, but it's easier for the compiler, as there's plenty of annotation about the layout of the code. Okay, now that we have the AST, we'll start going to the back end. The first part of the compiler backend is middle end optimization. When you optimize, you perform a series of passes, which are rules about optimizing the code. Some of these passes include dead code elimination, function call inlining, the virtualizing known interface method calls, and escape analysis. Let's look at some of the optimizations performed in the middle end. We'll talk about inlining and escape analysis. Okay, inlining. Whenever Go invokes a function, there's a lot of overhead since you need to read relevant information pertaining to that function and store that in memory. Inlining is a technique that attempts to reduce that overhead. It's basically a way to embed another function into a function that called it. If a function calls another function that is less than 80 nodes in AST representation, then GoLang decides to combine them into one function. This way, you don't have as much overhead as calling 2 separate functions into memory. Let's talk about another optimization technique, escape analysis. Sometimes a variable is used beyond the lifetime of a function. Now, these variables are typically stored in the stack territory of the memory, and if you try to access a variable, that no longer exists in the stack. So the entire program doesn't really function anymore. So you try to escape the variables into the heap territory. This way you can make variables accessible even after the functions disappear. The next part of the backend compilation consists of a walk. All that magic that makes GoLang easier to write is enabled because of walk. Here we decompose complex statements and desugar Go constructs. For example, a switch statement turns into a binary search or jump tables. Meanwhile, maps and channels turn into runtime calls. Now the AST is getting another makeover with SSA conversion. SSA stands for single static assignment and is a compiler technique to further optimize code. Let me explain more about SSA. It's a lower level intermediate representation. When you convert the AST into SSA, all the variables in the AST will become unique and immutable. This is why we get the name single static assignment. The reason we convert SSA is because it's easier to optimize code in SSA form. SSA in Go was first introduced in version 1.6 for AMD 64 platform, and then expanded to all other CPU architecture in version 1.8. Go is not the first to use SSA. It's been widely used in other compilers like GCC and LLVM. This is another case where it's easier to show than tell. Let's look at the code before and after SSA. Before SSA, you can assign values to a variable many times. However, when the SSA conversion happens, the variables become renamed to become unique. So if you try to reassign another value to a variable, you're not using that variable, but creating a new variable. This means no variable will be assigned a value more than once. Once you convert into SSA, the compiler performs another series of optimization passes. This time, the passes take advantage of SSA. These are the kinds of passes you can perform with SSA. Phi elimination, copy elimination, short circuit, decompose, fill optimization, nil check elim, prove, BCE, which is bounds check elimination, loop, DSE, dead store elimination, write barrier, insert loop, res checked, res checks, critical, likely adjust, layouts, flag allocation, region allocation, and loop allocation. You can see this all in the source code. Now, what I'd like to highlight CSE, or common sub-expression elimination, as it's one of the best passes to showcase the advantages of SSA. Common sub-expression elimination is a way to reduce redundancies in the code. For example, we have a code with variable y and z getting the same expression of x plus 2 assigned. It would be more efficient if we could just say x plus 2 once and use the variable that already has that value. But there's a problem. We don't know if the value of x plus 2 changes between the variable assignment x, y, and z. If we didn't have SSA, you'll have to traverse between y and z and see if the value of x changed. Now let's see the code with SSA. We don't know the value. We know that the value of x never changes, and neither does the value of y. So if you see z equals x plus 2, you know that at this point in execution, x plus 2 is still equal to y, and you could just assign z with y. If you're curious about how your code is transformed as SSA, the Go toolchain provides a way to inspect your code's representation during compilation. You can invoke with the Go SSA argument, which takes the function you'd like to inspect as a parameter. For example, in this command, you're looking at the main function. When you run this, you will get an HTML file with every step of the compilation. Here's how the HTML output looks like. So now that we got SSA, the final step is to have a machine code generation. This turns the SSA representation into CPU instructions. And at this point, the code becomes machine independent. The conversion into these instructions happen in the lowering pass in the SSA form. The SSA was abstract enough to be applicable to any kind of platform. However, once you lower it, the code becomes specific and dependent on the machine architecture. For example, in the ARM64 memory, memory allocations are possible, so the compilers can use some of the load store operations. As you can see, the lowering pass brings a lot of optimization that are available specifically for that architecture. Here are some of the final code passes. You have dead code elimination, you move the value closer to the point of usage, you remove local variables that are never read, you do register allocation, there's stack frame layout, assign the stack offsets to local variables, and there's a pointer liveness analysis, which compute which on-stack pointers are alive at each safe point in the garbage collector. And then there's object file writing. Once you have all the final passes, we finally write an object file that becomes a binary. The object file would contain data, export, reflection data, export data, and debugging information. So, we covered a lot, so I just want to have another round of bird's eye review. We got the source code, we got lexical analysis, we parse that, and we generate the AST. Once you get the AST, you go into the backend procedures, you do the middle end optimizations, which is a series of passes. We walk, and then we convert that into SSA, which is another series of optimizations. And then we finally generate the machine code with machine-specific optimizations, and you get the binary. If you want to learn more about compilers, the GoLang documentation provides a lot of information about it. I would definitely start with the first article, Introduction to Go Compiler. But there are also other external websites that provide a lot of information on compilation. A Journey with Go was great. Eli Bendersky's blog was very thorough. Hacking Go Compilers Internal was also pretty good. There's also a lot of information about SSA because it's an established technique in the compiler field of compiler research. There's an introduction to Go Compiler's SSA backend, the official Go documentation. One of the implementers of the SSA in the Golang team, Keith Randall, gave a talk about it, and it's very thorough and clear, so I'd recommend that. There's also another website on Dave Cheney's website, Inlining Optimizations in Go. It's also a good documentation. If you're also curious about other implementations of Go, there's one that describes GCC Go in the official documentation. You could also check out their GitHub repository. Outside of Golang compilers, if you want to learn more about compilers in general, I would recommend these books. The left one is the infamous Dragon book, which scares off a lot of people, including myself. But if you really want a easier way to start, then I would definitely recommend Crafting Interpreters, where you make your own programming language and really understand how you define the rules and make sure you have a program that follows those rules and convert that into binary. Well, that's the end of the talk, and thank you for listening.
Are there any questions?
I guess that for your talk, you explore the source code of Go, I guess, right?
I'm sorry?
You explore the source code of Go.
Right.
How do you find it? Is something that is, do you find it readable? Do you find it kind of relatively easy to follow, or?
So here's the, since I have a Python background, here's a big difference from a Python background. Python, the source code isn't as readable as Go code. I mean, it doesn't include a lot of comments, but there's a lot of documentation. And this is probably because of the popularity, the community, and also the legacy. So sometimes there's a lot of external tutorials that explain the compiler internals. Whereas with Go, there's not as much documentation yet. So you really have to go to the source code and read the explanations. And as you said in your talk yesterday, it's not as straightforward, but it explains a lot. And so long as you're willing to digest it, it does explain it in the source code. This is probably how the Golang gets a lot of contributors to join and understand the project.
Ciao, great talk. I didn't fully get the advantages of SSA, meaning to me, when I read it for the first time, it looked like it was creating a lot of memory allocation. So because you have to every time to create a new variable. So I didn't get it why it's improving so much the performance.
So here it is. The reason you'd like to have SSA is because if you don't have it, you have to go through the entire source code and check if the value of X changed. So that's a lot of computation. Whereas if you have SSA, structurally, you know that the variable is never assigned another value. So that means if you find another expression that's X plus 2, then you know that the X never changed. So you could just say, oh, X plus 2 is actually assigned already before.
Okay, but there is a huge trade-off, because then every time you need to allocate auto space for the variables, right?
Yeah, there is that overhead.
So there is a math. I mean, if I don't know about SSA and just keep writing A plus 2, A plus 3, A plus 4, I'm just allocating for
Yeah, if you didn't know about SSA and make your own unique variables, then SSA wouldn't like change your variables.
I mean, readability can, I mean, it's implicitly that there is a lot of, there is an overhead with every time I use readable variables.
Can you, there's a lot of advantage.
So there is a lot of overhead when I use readable variables.
Yeah, yeah, sure. You take a memory space when you, assign another variable. But I guess the Go developers find, especially with SSA, it does take a little bit more time on compilation, but they thought that it was just the right amount of compromise.
Okay, probably I could try it on my own, but I will try to ask you.
Sure.
What is the level of like the GCC versus GC optimizations at the level, at the backend, like level? Like the GCC compiler does a lot of optimizations probably because it does have decades of development, but the GC is newer, I would say.
So the reason GCC Go existed was in the earlier days of Go, the compiler wasn't as advanced and didn't contain a lot of optimization techniques. So in order to leverage GCC's infrastructure, they made a front end that would convert into GCC IR. And back then, you got to take advantage of GCC optimizations that weren't available in Golang. However, nowadays, the Golang compiler is pretty advanced, and they've taken a lot of influences from other compilers. So you got pretty much a lot of parity with Golang compilers and other compilers. As a matter of fact, if you're going to use Golang, you might want to use a GC, the official compiler, because it supports the latest features. Whereas with GCC Go, you're still back on the older versions, and there's no generic support. So it is a more of a if you really want on dynamic linking of libraries, you could use it. But otherwise, you could just get a fat binary and just make your life easier.
Yeah, definitely. I was just curious, like,
Yeah.
I will use GC.
Yeah, thank you.
That's all. Thank you, Richard.
Okay, thank you.